think that's meant for lunch.
As I was walking away, I heard someone growl. Caitlin doesn't like me. So, okay, so then I go. Okay, I'll use. I will chew. Yeah, chew meat from now. Wait, now you will then. No, but like, I like testing food.
Alright, I can't find it quickly. If I can find it, I'll show it to you guys next week. But it was some type of gum package that when you flip up or open it up somehow, like on the flap, it had an integral for you to solve.
Oh gosh.
I don't know. I saw it online. And I'm like, that's awesome, but I gotta find out where it is.
Like to most people though, like imagine like if you had no idea what, you've never seen it before. I don't know, it'd probably be like the weirdest.
Like, what is that, right?
Yeah, that's how whenever I saw it, I was like, almost too good.
Because I used to sit in the calculus class,
Uh-huh.
and I would see that, and I was like, and she expects me to do that someday?
Dang.
Like, that's not happening.
But it is.
Now here we are.
I know.
It's not that bad.
It's not that bad. Okay. This next unit that we're going to cover is probably, I don't want to say the most important of the Calc 2 course, but it is a big part. Like I said, we're going to spend a lot of time on it, okay? But the section we go over today is more of like an introduction to it, so I think you guys are going to find this fairly simple. We're going to build on it, though, as we go through the unit, okay? But we're going to talk about specific terminology and notation that we're going to see throughout this unit. We're going to take a look at sequences, series, and summation. I'm not sure if you've heard of these before or have seen specific notations before, but that's why we're going to go over it. So the first thing we're going to kind of discuss is the difference between a sequence and a series. They're very similar, but there's one slight difference that makes it very, very important in the difference between them. So if you take a look at a list of numbers, okay, a list. Notice how they're separated by commas. That's referred to as a sequence. So if you have numbers separated by commas, it's a list, aka a sequence. Based off of this particular sequence, we're going to try to identify particular terms in that sequence. So you see all of these little values, a sub 1, that's how we would read it, a sub 2, a sub 13, and then a sub n. Okay, n is just representing at any point in the sequence, where do you want to be located. It's a variable, so you can pick which spot you want. This a sub 1 is signifying the first term. So based off that sequence, what's the first term? The first number listed?
1.
We have 1. What about the second number listed? 3. What about the 13th number that would be listed?
27.
Close. 25. Okay. Now, when it comes to a sub n, notice how n is a variable. So we're going to try to come up with what's called a rule. You can think about it as an equation if you want to use that word. We're going to find a rule for this sequence. Okay, is there some type of equation looking setup we could use that we could simply plug in 13 and get 25 as an answer, or plug in 2 and get 3 as an answer? So this is going to be a lot of pattern recognition. So we're going to try to look for a pattern within these numbers. What are you doing to 1 to get 3? What are you doing to 3 to get 5? And so on and so forth. Can we find some type of pattern? You're adding 2 each time. Okay. So we got to think about how would that pattern maybe show up in the rule. Maybe there's more than one rule that could be written. Okay, I'm not saying that there's just one rule for every single sequence. It just depends on how you want to write it. So bless you, think about n as your variable. Maybe you want to use x instead. So if you plug in an x value of 1, you get out 1. If you plug in 2, you get out 3. You plug in 13, you get out 25. This 2 plays some part in it, Maybe not necessarily adding 2, but there is a 2 in the rule somewhere. Yeah.
So we need 2n minus 1.
2n minus 1. Okay, so let's check it out. If we plug in 1 for n, we get 2 minus 1, which is 1. If you plug in 2 for n, we'll have 4 minus 1, which is 3. Plug in 13 for n. You have 26 minus 1, which is 25. So it seems to check out. So even though the pattern was adding 2, notice how the 2 was actually some type of multiple, or being multiplied. So it's going to take some time for us to develop looking at a sequence, trying to identify a pattern, and then therefore using that pattern to write a rule. Okay, it's going to just take some practice and take some time. Let's try the next one. Can we list the first term in that sequence? 0, the second term, 1/2. The 54th term. Okay, so notice how this is a very large number within the sequence. We're going deep into the sequence. Maybe it would be better for us to identify the rule first. That way we can simply plug in 54 and boom, we'll get our answer. So can you find some type of pattern going on with those terms?
n over n plus 1, sorry.
N over n plus 1. All right, let's check it out. If we plug in 1, we should get 0. But if we plug in 1, we get 1 over 2, which is actually this one.
No, if you plug in 1, you should get...
You're on the right track.
So is it n minus 1 over n?
There we go. If we plug in 1, we'll have 0 over 1, which is 0. If we plug in 2, we'll have 1 over 2. Checks out. So if we were to plug in 54, we'd have 53 over 54. Looks good. All right, let's try this one. We'll write this one in. Oh, wait, nope, forgot to do that. We're working backwards now. I got a little ahead of myself. They give us the rule. You guys didn't see this, I'm sorry. But they give us the rule. So let's go ahead and try to figure out what the terms would look like. So to figure out the first term, we're just going to plug in 1, which would be negative 3. If we plug in 2 for the second term, we'd get 9. If we plug in 3 for the third term, we'll get negative 27. Plug in 4 for the fourth term, we'll get a positive 81, and you could keep going. Okay. What about if we wanted to plug in 100? We'd get out the calculator, but maybe we'll just represent it as negative 3 to the 100 for now. Okay? Are we doing okay so far? All right, so something we can do to relate this to kind of the improper integrals that we were working with in the last unit, we're going to take a look at whether these sequences converge or diverge. So the further you go into the sequence, are you getting closer and closer and closer to a specific number? Okay, that idea of converging. Or is your sequence kind of getting infinitely larger or infinitely smaller? Okay, meaning diverging towards positive or negative infinity. So maybe take a look at your list here, or think about if you were to continue using this rule, what would happen? Are we going to converge to a specific number, or are we going to go off towards some type of infinity? Diverge, definitely. We're basically adding 2 every single time, right? That was the pattern. So we're never really going to reach a particular number. We're just going to keep adding 2 every single time. What about for the next one? Converge to what? Can we maybe identify what it might be? 1. What about the next one? diverge, yep. Notice how the numbered values are getting larger. We're just bouncing kind of back and forth between positive or negative. Okay, but we are diverging. Good. Let's try the next one. Let's see, first term listed, we have 6. Second term listed is 8. Somehow we got to figure out a pattern to help us with the 19th term, or maybe some rule to write that would help us. So can you find a pattern between the numbers? Somehow, for your rule, if you were to plug in 1, you should get 6. If you were to plug in 2, you should get 8. If you look briefly at the sequence, you're adding 2 every time, so maybe you can think about what should be showing up in your rule. Very similar to the one above it that we did. Yeah. 2n plus 4, I like it. If we plug in 1, we get 6. If we plug in 2, we get 8. So if we plug in 19, what are we going to get? Yeah? 42, good. Okay. You're good. Converge or diverge? If we were to keep listing numbers, diverge, yep. All right, let's try the next one. So for this one, they give us the rule. They want us to list out some terms and identify ones. So if we were to plug in 1 for the first term, we would have -1 squared, which is 1. If we were to plug in 2 for the second term, we'd have -1 cubed, which is -1. If we were to plug in 3 for the third term, we'd have -1 to the fourth, which would be a +1. Plug in 4 for the fourth term, we'll get out -1. Okay, we could keep going if we wanted to. And if we were to plug in 44, looks like we'd get -1. Converge or diverge? Are we getting closer to a specific number? Are we going off towards an infinity? Or, so it's really like hard to determine neither of those, right? We know it's not, hopefully we realize it's not converging, right? We're not getting closer and closer and closer to a specific number, okay? So therefore it must be diverging, but it's not diverging in the sense of an infinity like we've seen so far. It's diverging because you are bouncing or oscillating back and forth between two values. You're not getting closer to something, okay, and you're not necessarily going towards an infinity, but you do have some type of oscillation between two numbers. Okay, so as long as you can say that it's not converging, then it must be automatically diverging. Okay, this is just a different reason for diverging than the infinities that we've discussed. All right, let's try the next one. So based off the sequence, the list of numbers, the first one's -100, the second term's 10. Can we figure out the 9th term? Or maybe we'll think of a rule first to help us with that. Somehow if you plug in 1, you need -100. You plug in 2, you get out 10. Can we find some type of pattern between the numbers, perhaps, to help us out? Yeah. Dividing by -10. All right, so that might show up somehow in your rule. Yeah.
-100 divided by 10 then.
-100 divided by 10. 10 to the n, like that. Let's check it out. So if we plug in 1, that would, bless you, that would give us negative 10, right, if we plug in 1, but not negative 100. You want negative 1,000 instead? So if we plug in 1, that would give us negative 100. If we plug in 2, that'll give us negative 10, right? But we want positive 10.
So would you put, so it would be 1,000 divided by negative 10, so that would be negative also.
Okay. How do you want to do it? Negative 10 to the n, like that?
Positive 1,000 on top.
Positive 1,000 up top. Okay. Notice how this one's oscillating too, right? Just like this one oscillated, you bounce back and forth. So we have some type of negative going on. Didn't this one, we were going back and forth between positive and negative? So we had some type of negative to a power going on. So maybe we have to use that here. So if we plug in 1, that'd be 1,000 over negative 10, so that checks out. If we plug in 2, it might just be how we write this, because in terms of order of operations, we do 10 squared first, and then...
It's supposed to be negative 10, that's just 2.
Yes, there we go. Okay, so if we square, there we go, if we square that one, this would end up being a positive 100, so 1,000 divided by 100 would give us 10. If we put in 3, that would be 1,000 divided by negative 1,000, which would be the negative 1, right? So it seems like it's checking out. So for the 9th term, maybe we'll just show that we're plugging in 9 for that power. It's going to be some decimal, 0.00000 something, maybe. Converging or diverging? This one's a little different. We are bouncing back and forth, right? Positive, negative, but are your numbers getting closer and closer and closer to something? Yes, closer and closer to what? To 0, okay? So I don't want you to get into the habit of looking for like positive, negative, and it's always diverging. That's not the case. Okay, you got to take a look at the numbered values themselves. Are you getting closer and closer and closer to something specific? Okay? We're doing okay so far? All right, so sequences are just a list of numbers separated by commas. Sometimes we can define a sequence based on a formula using previous terms. So what we did here is we simply used n as the variable, okay, where we'd plug in whatever term we want, and that would give us the value of that term. But if we're going to use previous terms, these are what are called recursive formulas. We're going to take a look at a few of those on the back page. Okay, so recursive. So we still have the same like a sub n's, a sub 1's going on, but a recursive is a little bit trickier to work with, because in order for you to figure out one term, you have to use the previous one or even 2 previous terms to help you out. So here's a quick example. They give us a rule, but instead of just having n in there as the rule, notice how they have a sub n minus 1. So if you're trying to figure out, for instance, the 5th term, okay, if you want n to be 5, you have to do 4 times the 4th term minus 3. Does that make sense? The one before it. If you did 5 minus 1, you get the 4 for the 4th term. But in order for you to know the 4th term, you had to do 4 times the 3rd term minus 3. And in order for you to know the 3rd term, you had to do 4 times the 2nd term minus 3. So in order for us to get here, okay, we have to start off knowing something specific, okay, one specific term in that sequence. So we're going to start off in this case with the first term of 2, and we're going to use this recursive formula to help us figure out the first 4 terms. So let's go ahead and try to list a sub 2. So to figure out a sub 2, we have to do 4 times a sub 1 minus 3. And notice how a sub 1 was 2. So 4 times 2 is 8, minus 3 would give us 5. In order to figure out the third term, you have to do 4 times the second term minus 3. And we just listed the second term as 5. So 4 times 5 minus 3, we would have 17. And the fourth term, we would need 4 times 17 minus 3, which I think would be 65. Do you guys think you can do the second one? Okay, they give you the first term and the recursive rule. Notice how it involves a previous term. You guys get 8, 4, and 2? Yeah? Good. Alright, let's try the last one. How does 2, 6, and 24 sound? Good? Perfect. Okay. So a very kind of popular recursive sequence is the Fibonacci sequence. Have you heard of that before? Have you seen it? Do you know what it is? No? Eric, you do? Do you know what those numbers are?
No, it's 1, 2, 4, 3.
Close.
It's like
1, 1, 2, 3, 5, 8, 13, and so on. Can you guys find a pattern within those numbers? Say it again. You add the previous 2 terms, okay? So in terms of writing a rule, okay, it would have to be recursive because you're using previous terms to help you figure out a new term. So let's say, for instance, we wanted to figure out a sub n, like maybe the 13th number in the sequence. You would have to add the previous 2 terms. So that would be a sub n minus 1, okay, the first term before this one, and then add the next one, which would be n minus 2. Hopefully that makes sense. Like if you wanted to find the 13th term, you'd have to add together the 12th and the 11th term, the previous 2. So that's kind of the recursive rule for the Fibonacci sequence. There is so much cool information about a Fibonacci sequence. It's one of my favorite things in math. And if we have time before the end of the year, I'm going to show you all the different connections with the Fibonacci sequence. One of my favorites. Okay, so sequences is just a list of numbers separated by commas. A series, on the other hand, is the sum of all the terms in the sequence. So no longer are they separated by commas. What are they now separated by? Addition, right? So if we have a sequence of 12, 15, 18, 21, the corresponding series would be 12 plus 15 plus 18 plus 21. So sequences and series are very, very similar. It's just whether it's a list of numbers or a sum of numbers. Do you have commas or do you have additions? That's what you're basically looking for. So to help us mathematically write a series, we use what's called a summation symbol. It's this Greek letter called sigma. Maybe you've seen it before. And it kind of acts almost like an integral. This n up top is your upper bound. And this k number or n number or whatever it might be down below is your lower bound. And the a sub k or a sub n, whatever letter again, in the middle is your rule. So in terms of this generic kind of written sigma here, or summation, you're going to start with a value of 1, and you're going to keep plugging in each integer up to n. Integer meaning a whole number. So if we plug in 1 for k, that would look like a sub 1. And then we're going to add what we get when we plug in 2, which is the next integer. If we plug in 2, we would have a sub 2. We're going to add the next integer we plug in, which would be a sub 3. And we're going to complete that process until we reach whatever upper bound we have, which would look like a last term of a sub n. Okay, so we're going to practice writing these series out based off the way this sigma looks. Okay, so for the first one, our rule is 4n. We're going to start by plugging in 0, we're going to end with plugging in 5, and we're going to add all of the other terms in between 0 and 5. So if you plug in 0, what do you get for your first term? 4 times 0, we have 0. We now need to add what we get when we plug in 1, the next integer, which would be 4. Then we have to plug in the next integer, which would be 2. So we would get 8. The next integer would be 3, so we would get 12. The next integer is 4, so we would get 16. The next integer is 5, and notice how that's our upper bound. So that's the last one that we're going to plug in, and we would get 20. Okay, so it says rewrite each series as a sum. We're going to leave it like this. Okay, we're showing how we're adding everything together. Let's try the next one. We're going to start by plugging in 1, and we're going to end by plugging in 4. So our p-value is 1. 1 to the first power is 1. We then have to add 2 to the second power, which would be 4. Then add 3 to the third power, which would be 27. And then we're going to end with 4 to the fourth power. Do we know that one? 256. Good. All right. We'll leave it like that. And the last one, we're going to start by plugging in 7, and we're going to end with plugging in 10. So if we plug in 7, we'll have 7 times 10, which is 70. Next, if we plug in 8, we'll have 8 times 11, which would be 88. Next would be 9 times 12, 108. And then the last one, 10 times 13. We have 130. We getting the hang of it? Okay. So the next one, notice how the directions are a little bit different. It says evaluate each series. So that word evaluation means to actually figure out or calculate. So after we list, I don't want to say list, because then you're going to think sequence. After you write all of the numbers with the addition, we're actually going to perform the addition. We're going to add everything together. So let's try our first one. We're going to start with 0, end with 4. 3 to the 0 would be 1. 3 to the first is 3. 3 squared is 9. 3 cubed, 27. 3 to the fourth 81. Okay, so that's where we stopped on the other examples, but since it said evaluate, we're actually going to add all those up to see what we get. What'd you get? 120, you said?
No, but probably you're right.
I think I got 121. Does that sound good? Okay, I'm going to show you how to type these in your calculator just in case, because sometimes these rules are going to get pretty involved. Okay, but I'll show you how you can use a calculator in a second. Let's try the next two by hand though. Okay, so we're going to start with 1, we're going to end with 4. We'll write down all of the terms and then we'll add them together. So if we plug in 1, we need -1 to the 0 power, which is 1, times 1 over 1. So if we plug in 1, we get out 1. Next we're going to plug in 2. -1 to the first power is -1 times 1/2 would be a -1/2. If we plug in 3, we'd have -1 squared, which is a +1, times 1/3. And then the last one, we'll plug in 4. So we'll have -1 to the third power, which is -1 times 1 over 4. So if you were to actually perform the summation, I think you get 7/12 after you get a common denominator for all those. Alright, let's try our next one. We'll start with 4, end with 7. So 4 squared, we got 16 divided by 2, we got 8. Let's see, 5 squared, 25 divided by 2 is 12.5. 6 squared is 36 divided by 2, we got 18. And then 7 squared, 49 divided by 2, we got 24.5. Okay, so if we add all those up, 63. Perfect. All right, I'm going to show you how to do these on your calculator. Do we have one handy? All right, I want you to hit, normally for derivatives and integrals we go to the math button, right? All right, hit the math button, and we know option 8 is derivatives on our calculator. We know option 9 are integrals on the calculator. Option 0, see how it says summation? Do we have that on there? Yeah? Go ahead and hit enter, and it should bring up that little sigma notation with your boxes. Okay? So for instance, number 7 example that we did, you can't really type in n, but we'll just use the variable x to represent the same thing. We'll say x is going to start at 0, we're going to end at 4, and our rule is 3 to the x power. And if you hit enter, you'll get 121. So it's going to give you the ending value, not necessarily the individual terms in the series. It's just if you were to add them all together, what would you get? Okay, so you can check the other two if you want to do that as well. So there is a summation option on your calculator. All right, let's try to write some of these summation rules, okay, using the sigma notation. So we're going to start with a k value of 0, but we're also going to try to think about how would the rule change if we had a k value of 1. So we're going to check out two different things, two different options. So take a look at this sequence. Well, it's not a sequence because we're not listing numbers. Take a look at the series, rather, and think about what rule you might develop to get each of those individual terms. Do you notice how we're bouncing between a positive and a negative each time? Do you see that? So what we're going to need is some type of -1 to a power, perhaps. So if we plug in 0, we want to get 1. If we plug in 1, we want to get a half. If we plug in 2, we want to get 1/3. 3, 4, 5, it looks like the ending number is 5, so that will be our top value. What can we multiply by? Do you see it, Eric? Yeah?
I guess I'm wondering why you have -1 to the k, because that your signs opposite what they are in the series you have here. Because your first term is positive, but if you plug in 1 for...
Okay, well, our first term is positive, right? But I need to plug in 0 to give me the first term.
Oh, I see.
So if I plug in 0 here, that would give me a positive value, right? Okay? Yep. So somehow I need to plug, if I plug in 0 for this k, this is going to become a +1, right? So +1 times something needs to still give me a 1. So whatever I write in here, and I plug in 0 for k, this has to be 1. Notice how if I plug in the number 1, like for the next term, -1 to the first is -1. Okay, so I have that negative sign showing up here. But whenever I plug in 1 into this value, I should get 1/2. Can we think about it? We're dealing with a fraction, so maybe that might be a good place to start. Let's try it. If you plug in 0, you get 1/1, which is 1. If you plug in 1, you get 1/2, which is 1/2. If you plug in 3, sorry, if you plug in 2, you'll get 1/3, which is the 1/3. The -1 out front is helping it go back and forth between a positive and a negative, because the power that we're using is going to make it bounce, right? So here's what the summation would look like if you wanted to start with 0. How can we write a different summation for the same exact series, but this time starting at 1? So if I plug in 1, that's now representing my first term, not if I plug in 0 to represent that first term. Yeah? Okay, so 1/k, 1/1 would give me 1. If I plug in 2, 1/2, I need it to be negative though. So I still need some type of oscillator, if you want to call that, out front. Okay, what? -1 or +1, something like that, right? If you plug in 1, we'll have -1 squared, which is +1, times 1, which is 1. If you plug in 2, we'll have -1 cubed, which is going to make it negative, and 1/2, which would give us the 1/2. So that one looks to be correct. So notice how the summations might change, okay, depending on the starting value that you want. The ending value for the second one would be 6, because if you start with 1, you have 1, 2, 3, 4, 5, 6 terms. Okay, we'll try 11 as an example on Monday, all right?
Mrs. Bowden, do you
Yeah.
think you'll have your baby really?
I don't know.
We
were all like,
we thought you
we
had
thought
it
you had
yesterday.
it, and then we were all like, let me got it on the test.